All right, so we're going to combine these two. So we end up with 3 copper solids plus 2 nitrates plus 8H plus 6 electrons yields 3 copper 2 ions plus 6 electrons plus 2 NO gas plus 2 H2O liquids. You notice the 6 electrons cancel, 6 electrons, 6 electrons. Then we need to figure out what the driving force, if any, is. To figure out the driving force, we want to go from stronger to weaker. And so we have to label these. The copper was the reducing agent. The nitric acid is the oxidizing agent. The copper 2 is our oxidizing agent on the right. And the NO with H2O is our reducing agent. And then we go to the chart and we look. What's a more powerful oxidizer? Nitrate and H plus or copper 2? So here's copper 2, here's nitrate and H plus. So it looks like nitrate and H plus is a stronger oxidizer than copper 2. So this is the stronger oxidizer, nitric acid. And this is the weaker oxidizer, copper 2. Then we do the same for the reducing agents. The reducing agents, copper metal versus NO and H2O. Copper metal is closer to lithium. Copper metal is a stronger reducer. So this is a stronger reducer. This is a weaker reducer. And so we have driving force here, going from stronger to weaker. And so we could just rewrite this to clean it up and see if we can cancel anything else out. But it looks like that's good. And so the net reaction is 3 Cu solids plus 2 nitrates plus 8H plus yields 3 Cu2 plus 2 NO gas plus 2 H2O liquid. Stronger RA, stronger OA, weaker OA, weaker RA. And driving force. All right, so unlike single replacement, which we got no reaction, in the chart method we do get a reaction. And these would be the products here. All right, so again, for the chart method, you don't have to overthink it. That is, you don't have to understand why something's better than something else. You just have to be able to use the chart to rank things. And once we do that, then we should be able to predict the products. Such. Now, there could be subsequent reactions. So for example, when you do this is a reaction shown in a picture in chapter 5. It produces a brown gas. NO is a colorless gas. And so there's a second step that occurs. And so step 1, we have this. And step 2, the NO reacts with air. That is oxygen in air to form NO2. So this would be another redox. This would be like complete combustion, but this is what happens when we do that. So if you take some copper, put some nitric acid, you get the brown gas. The brown gas is a result of the oxidation of nitric oxide to nitrogen dioxide here, the second step. All right, there's some more examples of redox, but let me skip those so I can jump ahead. Potential diagrams, here we're looking at, so for example, when we do combustion, can you predict how much soot I'm going to get, how much carbon monoxide I'm going to get, and how much carbon dioxide I'm going to get? Now, it's kind of complicated, right? It depends on, the fuel-to-air mixture and other things, how much yellow you got in the flame, etc. Well, the same thing here. Are you going to predict? Well, some of these things, depends on how vigorously you react them. You could take permanganate and go all the way to manganese metal or manganese 2+, or somewhere in between. And so this is just showing all the multiple products that you can have depending on how strong of an oxidizer, how strong a reducer, and how vigorous the conditions are. And so the redox reactions can get quite complex. Because, especially for manganese. Manganese has oxidation states ranging from +7 to +6, +5, +4, +3, +2, 0 to potentially negative in the gas phase. All right, so we aren't going to do anything with potential diagrams because that's going to up the complexity of ours, but it would increase the accuracy of our predictions. Okay, the last thing is skeleton redox. Skeleton redox, everybody's probably done these before because these are in chapter 5. Skeleton redox is the procedure where you separate it into skeleton half reactions. For each half reaction, you balance all elements other than hydrogen and oxygen. You balance oxygens by adding water. You balance hydrogens by adding H+. You balance charge by adding electrons. You double check, then you combine the half reactions, etc. The difference between the chart method and skeleton redox is, in skeleton redox, you're given the major products. And so, for example, here are the major products. In the chart method, you aren't given these. And so it depends on the conditions. For example, does ethanol combust? Does ethanol burn in oxygen? Yes, ethanol burns. Ethanol is highly flammable. But ethanol doesn't always have to burn or burn completely. For example, have you ever heard of wine turning into vinegar, right? That's actually very common because ethanol in wine gets partially oxidized to acetic acid under the right conditions. And so here we have it. Permanganate's perfectly capable of oxidizing ethanol all the way to CO2. But what if we just partially oxidize it? In other words, what if we have mild conditions? If we have mild conditions, it might not fully oxidize the ethanol. In other words, we might get the right conditions that produce acetate or acetic acid. Okay. This would be acetic acid if we're under acidic conditions. This is under basic conditions. And so here we're just having incomplete oxidation of ethanol. Well, these redox reactions are quite complicated, and they depend on how vigorous the reaction is carried out and other factors, concentrations and stuff. And so for skeleton redox, you just mix it together and see what happens. So they mixed it together and they found out they formed acetate rather than CO2 or whatever else, carbon monoxide, soot. And so under these conditions, this is it. But we don't have the whole reaction here. This is only part of the reaction. This is what we call skeleton because there's things missing here. And so what's missing? Well, what we do is we split this up into two half reactions. Do you remember doing this? And then continue. And so for the homework set, you're going to be able to finish all those reactions either using metathesis, the double replacement style, the Bronsted acid base, or the chart method for the first 15. I think the last 5 are skeleton redox. All right, any questions on that? Do you want to do another example or 2 examples of the chart method, or do you just want to start working these out on your own? More examples? Chart method? All right. Let's do some more examples of the chart method. Potassium is carefully added to sodium chloride. All right, potassium is carefully added to sodium chloride. Is potassium, what is that? Solid, liquid, or gas? Solid. Potassium metal. Sodium chloride solution, NaCl, AQ. Oh, this looks like an A plus BX, doesn't it? This looks like an A plus BX. Oh, this is single replacement, right? Wrong. If you did the single replacement, you would have the wrong answer. And so this is why I didn't even bother covering single replacement in Chem 1A. We went straight to the chart. Even though we went straight to the chart, I saw plenty of wrong answers. And so we would handle this by the chart method. The chart method is first we inventory. Potassium is just potassium. Sodium chloride is a strong electrolyte. So we get sodium ions and chloride ions. Is that it? And water. H2O liquid. Okay, then we go to the chart. Potassium. What is potassium? And so let me bring up the chart here. Well, potassium should be easy because potassium is the #2 ranked reducing agent. It's a powerful reducer. And so potassium is a reducing agent. And then we have sodium ions. So if we look at sodium ions, sodium ions is #4 from the sodium metal is #4 for the reducers, but do I have sodium metal or do I have sodium ion? I have sodium ion. I don't have any sodium metal. I got sodium ion, which is #4 from the bottom. In fact, it's a pretty weak oxidizer. But anyway, it's an oxidizer, so we'll label it. Chloride. Chloride is here. Is chloride near the top? No, chloride's near the bottom of the reducers. But still, it's a reducer. So, is chloride the same thing as chlorine? No. You know, chlorine's a green gas. Chloride is just an ion that occurs in salt. And water. Water is both oxidizer and reducer. So let's figure out.
Why did we add water to all of our reactions?
Why? Because if you have salt water, what's the species most abundant in salt water? Is water. If water were completely inert, like argon or krypton or something like that, then we wouldn't. Actually, is krypton inert? How about xenon? Is xenon a really inert gas? No, unfortunately, xenon reacts with some things. And so the reason we add water is because 99% of the time it doesn't react, but that 1% of the time might be worth 10 points. And you don't want to lose 10 points on a 100-point test, right? And so a lot of people get in the habit of didn't react here, didn't react here, didn't react here. But pretty soon they say, I don't want to waste my time. And they stop putting it on, and then they get hit. And it reacts. Like here. They get hit. The reason I put this one on is, as we'll see, is this. The reducing agents, we have three, potassium, chloride, and water. Which is it? It's potassium. You know, chloride versus water. Chloride's even worse than water. Potassium is good. Potassium is good and strong. Oxidizing agents. So fluorine's the best. Let's keep going down from there. So we got sodium ions versus water. Here are sodium ions, right here, right? Sodium ions are here. Wow, water's at the bottom. And so it looks like sodium ions are a better oxidizer than water, right? Right? Wrong. Why is that wrong? Water's at the bottom. Because this is a subchart and within a chart. And remember this is minus 0.828, which means that water's not really here. Water is here between zinc and aluminum, which means that sodium is weaker. Water is stronger. So the strongest oxidizer is water. And then somebody says, well, what happened to sodium chloride? Nothing, and nothing's going to happen to it because sodium chloride is a spectator in this reaction. It doesn't participate. What's going to react is potassium. Well, what happens when potassium reacts? When potassium reacts, I just copy it down here. My reactant isn't K+. My reactant is K. So I'm going to take this equation and flip it so that the reactant is now K. So I flip it. K solid goes to K plus an electron. Now H2O is my oxidizer. I'll just copy it. This is right because H2O is my reactant, so I'm just going to write 2 H2O liquids plus 2 electrons yields H2 gas plus 2 hydroxide AQ. AQ I just leave off. So now I have to add up these two half reactions. The first one produces 1 electron, the second one consumes 2 electrons. Yeah, so we'll multiply the top one by 2. So 2, 2, 2. So now I produce 2 electrons and consume 2 electrons. The electrons must cancel. You cannot be left with electrons in a net ion equation. And so the reaction here is, before I do this, well, actually I'm going to just add them up. 2 potassium solids plus 2 H2O liquids produces 2 potassium plus hydrogen gas plus 2 hydroxides. I forgot to mention earlier that we always check to make sure it's balanced, because sometimes when we do this multiplication we screw it up, we screw up the addition. So when I make sure it's balanced, I look at the atom balance. 2 potassiums, 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens. So the atoms are balanced. But whenever you check the balance for net ionic equations, you also have to make sure the charge is balanced. So the net charge on the left is 0. The net charge on the right is 0. And so the charge is balanced, the atoms are balanced, it's balanced. Am I done? I'm not done because I didn't show the driving force. What is the driving force? Well, it's stronger to weaker. I know that potassium is my reducing agent and water is my oxidizing agent. But going backwards, what is what? Now going backwards, what is the easiest thing to do is look at the conjugate pairs in the half reaction. So if potassium is my reducing agent, then it's going to form the conjugate oxidizing agent. So potassium ion must be my oxidizing agent. And if water is my oxidizing agent, then the conjugate would be hydrogen and hydroxide. Hydrogen and hydroxide must be my reducing agent. So the combination of hydrogen and hydroxide is my reducing agent. And then I compare. Let's compare the two reducing agents, potassium versus hydrogen and hydroxide. So here's potassium. Where's hydrogen? Gas and hydroxide. I was looking up, but it's not up, it's down. It's here. Here's hydrogen and hydroxide. So if hydrogen and hydroxide are down here, potassium's here, then which one's stronger?
Potassium.
Potassium, because hydrogen and hydroxide actually belongs between zinc and aluminum. And so potassium's stronger. If the reducing agents follow this pattern, the oxidizing agents must. So let's double check it. That means water must be a stronger oxidizer than potassium ions. So here are potassium ions. Water is down here, but the water doesn't belong here. Water actually belongs here. And so water is indeed a stronger oxidizer than potassium ions, meaning we're going from stronger oxidizer to weaker oxidizer, and we have driving force. And so did the sodium chloride do anything? No, the sodium chloride didn't do anything. Sodium chloride was there to trick you into thinking it's going to react, but it didn't react at all, right? At all. Especially with A plus BX, you're so tempted to react it because it looks like such a tempting reaction. K plus NaCl, I'd say about 1/3 of the exams I get, people write this. It's going to form Na plus KCl. 1/3 of the people write that, typically. Chem 1A. Chem 1B, that percentage should go way down. All right, that's potassium plus aqueous sodium chloride. When methane burns, if you burn methane, what are you going to form? CO2 and water, right? But what about carbon monoxide? Is it possible to burn methane and get carbon monoxide? Yes. People burn methane and get carbon monoxide. It results in deaths every year, because they don't get enough O2 in there. And so when multiple products are possible, which one do you pick? You pick the one that shows complete reaction. And so when you do this, you always predict CO2 because it's complete combustion, right? Well, this, if I take ethanol and permanganate, I could make vinegar. I could take the ethanol and convert it into vinegar, right? No problem with that. But under the right conditions, you can take it all the way. If ethanol is completely combusted, do you know what it forms? If you were to burn ethanol completely, it would form carbon dioxide. And so when we're left with a choice, you always take it all the way. And so this is a redox chart example, which I labeled experience. This one is a level harder. This one would be like an advanced problem in Petrucci, right? And so this problem is a challenged one. It's also on your homework too, so I think. So it might not be too bad. All right, for the skeleton, let's just look at some of these. Ethanol goes to acetate, permanganate goes to MnO2. This half reaction split. Let's look at this one. This one's very weird. HS minus goes to S2O3. What does HSO3 go to? How can I split this up into two halves? Well, it turns out that some species can react both as the oxidizer and the reducer. You know, do you recall that one where we had hydroxide plus hydroxide? One of the hydroxides was the acid, the other hydroxide was the base. This one is going to be both. This is both the oxidizer and reducer, so we need two of them. HS minus goes to one of these, and HSO3 minus goes to another one of those. And we split it that one. Some of these are a bit tricky. And so AS2S3, well, arsenic goes to this. Where does the sulfur go? Well, it must go to this. So AS2S3 goes to these first two. Nitrate goes to the third. These are for splitting into half reactions. Okay, chromium and iodine. Chromium ends up here, iodine ends up here. So CRI3 goes to this and this. But where does hydrogen peroxide go? Hydrogen peroxide goes to blank because we don't have to worry about hydrogen and oxygen. Hydrogen and oxygen always balances out because we add water and we add H+. When you burn methane, don't go spraying ammonia in there. When you burn methane, right, don't spray ammonia in there because you're going to make some nitrogen-containing compounds like potentially. So methane combusting with ammonia yields hydrogen cyanide and water. Hydrogen cyanide is very toxic. And so anyway, we'd split this up. Methane and ammonia goes to hydrogen cyanide, O2 goes to water. That's the way we'd split that up. All right, those are just some hints to get you started on the homework, but just work on the homework. If you guys have questions over the weekend, you can post those on Piazza. And if you see a question that you know the answer to, go ahead and answer it. Okay, so I don't get to it. But anyway, I'll be here for a little bit, so if you have additional questions, you can ask me. Oh yeah, the next test is going to be Thursday. Next week, chemical reactions. Only chemical reactions.
For the one we did yesterday, when we did the catalysis for H3PO4 and sodium hydroxide, we got a reaction because there was a gravity force. We also got a reaction on the bottom side, so which one would be the right one?
It depends on what I ask. Yeah, in general, you just do it the metathesis way. For something like that, if it fits the AB plus CD pattern, just go ahead and do it the metathesis.
And it would kind of the answer.
Yeah. If you did it the other way, I would have given you credit as well.
Did the person show up?
No, the person didn't show up, so you're okay.
Am I in?
Yeah.
Yay.
Do you know how to do this with the sticker?
No. The person didn't show up for 3 days.
I didn't get any emails or anything like that, so. When you try to register for the class, it's going to ask you for an authorization number. So use that to get in.
Okay.
Okay.
On my ECC.
On my ECC. I have a set of instructions, but I guess I ran out of the car. It's just a piece of paper. But try it. I think it should be pretty self-explanatory. I think.
Thank you.
If you have trouble, talk to me on Monday.
Okay. Thank you.
Right. Oh, charger. Does anybody know her?